Bismillahirrahmanirrahim. In previous lectures, we have developed a new concept of probability, according to which probability exists before the occurrence of a random event, but is extinguished after it occurs. In this lecture, we will develop the rules of how we make calculations with these probabilities. So the first thing to note is that probability is about the future, what might happen. So we are standing at a certain point in time, and then we assess the central 50% of the probabilities. These are the most likely 50% events. So this may be a collection of things which can happen. I have just one arrow, and so this will cover the middle 50% of the possible events. After that, we have slightly less likely, 40% more events, 20% on either side, or it can have other geometric configurations. So at that point, if we consider the central event and the likely events, then we have a range of 90% of the possible events. If we want to go further, we can add 2% more on both sides and get to 99% probability. And now this range of events, the central ones and the likely ones and most of the unlikely one, covers 99% of what might possibly happen. And finally, we have these rare events, which are 0.5% on each side, total combined probability 1%. These numbers are just arbitrary qualitative numbers, and these ranges could be changed according to the application. In the 1930s, there was a battle about describing or defining what probability is. In this battle, Keynes and Knight took the position that the future is uncertain, we don't know what will happen. As opposed to this, Ramsey and De-Finetti took the position that all of the possible events would be known and their probabilities would also be known. And rational behavior would be possible only if this is true. Now, unfortunately, Ramsey and De-Finetti won this battle, and the theory of rational behavior under uncertainty follows this assumption that everything about the future is known. We know all the alternatives and we know all the probabilities. Now, the global financial crisis and many other such events show that this rational behavior under uncertainty theory is completely false. As opposed to this, Keynes thought that investors make decisions based on guesses about the future which are not really anchored with reality. Although this topic is of extreme importance, we will study the simplest possible cases where these considerations do not apply. As a general principle, a probability is a mental model of structures of external reality. We can never know these hidden structures of reality, and we can never know the future. We only have models of these future outcomes and probabilities. So we never have knowledge in the sense of justified true belief, which is one of the standard philosophical models of what knowledge means. And this is why models of the type that I am going to describe here have not been developed, because they don't match up to the standards we require of knowledge. Here there is a subtle distinction between subjective and objective and what we mean by these two terms, but I don't want to get involved in these controversies, and we will just develop basically an intuitive characterization without discussing the finer philosophical details. So a probability model is just a branching tree which gets more and more branches in time. So here we start at t at 1. We are in a fixed position, which is a deterministic world. Everything is known. But at time equals 2, there are 3 possible events which can take place. We don't know the probabilities, but we can probably assign probabilities to the different possibilities according to some calculations which may be more or less reliable. So a model we create for the future assigns events which will happen in the future and also assigns probabilities to these events. on a number of different bases which we will not discuss right here. Then after the second event takes place, that is after time equals 2 happens, one of these three events will take place. So then the future will depend on which one takes place. So for example here, if the top event takes place, then it will have further branches going out further in time. If the second event in the middle takes place, that will have further branches. And if the third event takes place, that has just one branch in this particular model. But this is what probability models look like. Then we can go to the fourth stage where the top event has two forks, and one of the events in T of 3 has 3 forks, and another one has 2, and so on. So this is what probability models look like. These are models where at every point we have some branches which go into the future, and all of those branches have further branches which go further into the future. So a tree, which is our model of probability, consists of nodes and branches. Each node is situated in time. It belongs to t equals 1 or t equals 2 or t equals 3. Each of the branches carries a probability. What is the probability that you will travel on this branch going from the previous node to the next node? This probability is conditional on your being at the previous node, but you may never get there. So the only thing we have is the conditional probability. If you are at a node, the sum of all probabilities going out of that node must be 100%. What this means is something must happen. One of the possibilities that you have listed, one of them must occur. Probabilities vary with time. So currently, if we are looking at what will happen in the future, then at t equals 0, maybe let's say there are two possibilities, the red one on top and the black one on the bottom. So the red one will happen with say 60% probability, and the black one will happen with 40%. So the sum of these two is 100%. So when we are sitting at t equals 0, these two events have these probabilities, 60 and 40. But when we come to time equals 1, then only one of these two events will have happened. Either we will be on the red branch or we will be on the black branch. So accordingly, at t equals 1, the probabilities change. At the t equals 1, either the red branch has 100% probability or it has 0%, according to which of these two events happened. Then as we go further, if we are on the red branch, then all of the black branches going forward have 0 probability. And we now have 100% probability at t equals 1. And so future branches carry on future branches. When we evaluate time in the future, the red event will always have 100% probability at t equals 1 or after it. Before it had only 60%, but after it has 100%. So this is what I mean, that there are different times and the probabilities change according to the time. When we use the tree as a model, a node is called an outcome. This is something which happens. And the branches carry the probability of that outcome. If an outcome is several branches away, then to calculate the probability of the outcome, we multiply the probability of the branches which lead into that outcome. If there are two outcomes in different branches, these are mutually exclusive. Only one of them can happen. If the other one happens, then both of them cannot happen at the same time. And now an event is something which can happen on multiple branches. So to calculate the probability of event, you have to calculate the probability of all the nodes on which this event happens. And as long as the nodes are mutually exclusive, you can add the probabilities. If two nodes are on the same branch, that means one of them happens first in time and the second one happens later in time. So in this situation, you cannot add probabilities. You have to identify the first node at which the event happens and use that. To get some practice in analyzing time branching tree models of probability, we analyze a very simple model. Here I have an urn which has two balls and two red and two black balls inside it, and these are shuffled up randomly, and I pick one ball out at random. So at the first shot I can either pick one red ball or one black ball, and both of these have 50% probability. So at time t equals 1, I will either have picked a red ball or I will have picked a black ball. Now on the top, both of these are equally likely, 50% event. Now in the top circle where I have picked a red ball, there's only one red ball and two black balls left. So whereas in the bottom circle, there are two reds and one blacks. So going forward from here, it matters which choice I made on the first draw. So if I made the first draw where I drew a red ball, then the probability of picking a black ball is now 2/3, and the probability of picking a red ball is 1/3. So this is what's pictured in the top tree. In the bottom part, if I picked a black ball to start with, then the probability of picking a red ball is now 2/3, but the probability of picking a red ball is 1/3. So we can calculate these probabilities. At t equals 0, probability of red or black is 1/2. At t equals 1, if you are on the red branch, the probability of the second pick being red is 1/3. On the black branch, the second pick being red is 2/3. Now suppose we go back to t equals 0 and ask what is the probability of a red ball on the second round. So now we are going one step beyond the immediate tree. So we are going 2 steps forward. Now we have to calculate all the possible ways in which red can happen on the second step. There are 2 possible ways. One is to pick a black ball first and then pick a red ball, or to pick a red ball first and then again pick a red ball. So these 2 ways have different probabilities. We just calculate the probabilities of each of these nodes by multiplying the probabilities. So the top node, which is red followed by red, is 1/2 times 1/3 is 1/6 probability. The bottom node is one black followed by one red. That has 50% probability, 1/2 on the first branch, and then 2/3 probability on the second branch. So that is a 2/6 probability. Adding both of these up, we get 1/2 probability of picking a red on the second ball at time t equals 0. At time t equals 1, this is no longer valid because now you will be on either one of the 2 nodes. So at time t equals 1, the probability of picking a red ball will either be 1/3 or it would be 2/3. So this is a time varying model of probability where the branches and trees tell us at what time what is the probability. Next, we consider an application that was considered in the first lecture of drawing straws. So we have n people and we have n straws. One of the straws is short, all of the others are long. We hold these straws out at random to the first person who draws a straw. If he draws the short straw, he is chosen. If he draws the long straw, then the turn passes to the second person. This keeps on, people keep on drawing straws until one of them draws the short straw, in which case he gets chosen. So what is the probability of being chosen? Is it possible that the sequencing matters? Maybe it is helpful to go early if you want to be chosen, or maybe it's helpful to go late, or maybe all the probabilities are the same. So this is something that we want to calculate. In doing such calculations, it's always best to start with the simplest case. Now, the case of 2 straws is trivial and it's left for the student to figure out for himself. Both people have 50% probability of being chosen. Now, suppose we take the next most difficult case, which is 3 people, A, B, and C, and there are 3 straws. I'll label them L1 for the long first straw, the long second straw, and the third straw is the short one. So L1, L2, and S3. So at the initial stage, person A will draw, and he can draw the L1, the first long straw. That means he is not chosen. L2 and S3 are left to draw, and it is B's turn. Or he could draw L2, in which case L1 and S3 are left, and he is not chosen, and it is left for B to choose. Or he could draw the short straw, which ends the game, and A gets chosen. So the probability of A being chosen on the first round is 1/3. Now we go to the second round where B will draw. So B will draw L2 on the top branch with 50% probability, and S3 with 50% probability. So if B draws the long straw, then C gets chosen, and the conditional probability on this branch is 50%. If B draws the short straw, he gets chosen, and that's also 50%. So either B or C will get chosen with 50% probability on this branch. On the other branch where A has drawn L2, the things look pretty much the same. There is a long and a short straw, and B can draw the long straw, in which case C is chosen with probability 50%, or B can draw the short straw, in which case B is chosen with probability 50%. At t equals 0, before any draws have been made, you can calculate that the probability of A being chosen on the first round is 1/3. And on the second round, C can get chosen in two ways. And both of these ways have probability 1/3 times 1/2, which is 1/6. So probability of B is 1/6 plus 1/6, and also probability of C is 1/6 plus 1/6. So both of these are 1/3 events. So standing at t equals 0, all three events, A chosen, B chosen, C chosen, are equally likely. All of them have probability 1/3. If you get to t equals 1, that means that A was not chosen, and you are still drawing. So now the probability of A being chosen is 0 because he drew the long straw, and now B and C have equal probability 50% at t equals 1. And at t equals 2, all draws have been made, and something or the other has occurred. Either A was chosen on the first round, or B or C was chosen in the second round, and there is no probabilities left at this stage. Having solved the problem with 3 people and 3 straws, it's easy to solve the problem with 4 people and 4 straws. We just start from the origin, and we know that 1/4 probability A will draw the short straw and will be chosen. And with 3 probabilities, 3 out of 4 probabilities, A will draw a long straw and will be out of the game. Now at this point, there are 3 players, B, C, and D, and there are 3 straws. So basically it's reduced to the case of 3 people with 3 straws, and we've already done the calculation, so we know that there are 3 equally likely possibilities that B will be chosen, or C will be chosen, or D will be chosen. So by using the rules of probability, we can see that all 4 possibilities are equally likely. All 4 have probability 1/4. The two-step probabilities are 3/4 for the first step, and then 1/3 for the next step. So the probability of 3/4 times 1/3 is 1/4. So all 4 possible outcomes have equal probability 1/4. Now we will use the solution to the straws problem to solve a problem which initially looks different but actually has the same structure. And this is about a housing lottery in which students are assigned numbers, which creates a ranking according to the numbers the students get to choose first. When I was an undergraduate at MIT, this is exactly how it actually happened, that the housing office would assign numbers to every student at random. Anybody who showed up at the housing office would get a ticket with the number on it, and the lower numbers, the first number would get to choose first, and the second number would get to choose second, and so on. So what used to happen was that students would line up at the housing office early in the morning because they were hoping to get the low numbers on the tickets. Now, is this a sensible procedure? Do you have better chances of getting low numbers if you show up early in line? Think of ticket number 1, the first priority, as the short straw and the other 999 as the long straws. Then, according to our analysis with 1,000 people and 1,000 straws, all people have equal chances of getting the short straw. So it means that all of the 1,000 students have equal probabilities of getting ticket number 1. And the same is true for all numbered tickets. So it means that all students have equal chances of getting all tickets at the start. And so it means that there is no sense in going to the housing office early in the hope of getting a low numbered ticket. So in this lecture, we have calculated the probabilities for branching trees across time. There are some very simple rules. Probability is only for future events. As time passes, the future becomes present and past, so the probabilities also change accordingly. At each node, the probabilities of branches going forward is conditional on getting to that node. Probabilities going out multiple steps in the future are calculated by multiplying the probabilities on the branches. And events which occur on multiple branches in the future, the probability is calculated by adding the probabilities of all the nodes on which the events occurs. So these rules allow us to calculate all the probabilities that we need. As an exercise in applying the rules of probability, we give you an exercise which has a very similar structure to the case that we have done. An airplane has n seats and n passengers. Everyone has been assigned one seat, but the first player goes in and randomly chooses a seat without ignoring his assigned seat. He has a 1 in n chance of sitting at the correct seat and n minus 1 over n chance of sitting in a wrong seat. After the first passenger, everyone goes to his assigned seats and sits in it, except if the passenger finds that his seat is occupied. If the seat is occupied, then he chooses at random from any available seat. So now the question is, what is the probability that the last passenger gets to sit in his assigned seat? So this is very easy to solve when n is 2 and when n is 3, and then it's easy to work up from there. So this is just to give you exercise.